Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will understand about this power factor in the electrical circuits and the electrical systems. So we will see what is this power factor, what is the significance of this power factor in the real systems, what is leading and lagging power factors, and if we have a poor power factor in our system, then how to correct this power factor. So simple by definition, this power factor is the ratio of true power divided by the total power or the apparent power. So first of all, let us understand what do we mean by this true power and the apparent power. So at our home and offices, we used to receive this power through the substations using the distribution lines, and we are using this power to power up our appliances. Now this true power is the actual power which is being utilized to power up these appliances, or in another way we can say that it is the power which is being utilized for doing some useful work. So let us understand this true power by taking the example of an electrical fan. So in case of this electrical fan, the true power is the power which is being utilized to run this fan, or to say it is the power which is being required to rotate the wings of this fan. So now if you see this true power, it is the fraction of the total power which is being supplied to this device. So apart from the true power, we also have a reactive power. So as its name suggests, this reactive power is being utilized in the reactive element of the load. Like here in case of this fan, this reactive power is utilized in generating the magnetic field inside the motor of this fan. So this reactive power does not contribute in generating some useful work, but still it is required to generate the magnetic flux so that the motor of the fan can be rotated. So in this way we have a total two components, the true power and the reactive power, and the vector sum of this true power and the reactive power is known as the apparent power or the total power. Now generally this true power is being denoted by the symbol P, while this reactive power is denoted by the symbol Q, and this apparent power is denoted by the symbol S. So now let us understand about these different powers and the power factor by taking one circuit example. So first of all, let us say we have a purely resistive load which is being connected to the AC voltage source, and let us assume that the value of this load is 40 ohm. So the current I which will be flow through this resistive load I will be equal to V upon R, that is equal to 240 volt RMS voltage divided by the 40 ohm, which will come out as a 6 ampere RMS current. Now in the earlier video of phasor diagram, we had seen that for the purely resistive load, the voltage and current will be in a phase. So if we see the waveform of voltage and current, then it will look like this. So as you can see here, both voltage and current are in a phase. Now whenever we multiply this voltage and current, then we will get the power that is being dissipated across the resistor. So the waveform of power will look like this. So now as you can see here, this power is always greater than 0. That means the entire power is getting dissipated across the resistor. So in case of the purely resistive load, the entire power is converted into the useful work. So in case of this resistive load, the power P will be equal to I square into R, that is 6 square into 40 ohm, which will come out as 1440 watt. Similarly, now let us say we have a purely reactive load which is being connected to the voltage source, and let us assume that the value of this reactive load is 40 ohm. Now for this purely inductive load, the current I can be given as 240 divided by J40, which will come out as 6 ampere. So as you can see here, in the case of purely inductive load, the current will lag the voltage by a 90 degree, and if we see the waveforms, then the waveform will look like this. So as you can see here, the voltage leads the current by a 90 degree, and if we multiply this voltage and current, then the waveform of power will look like this. So as you can see here, in the first half cycle it absorbs the power from the load, while in the next half cycle it supplies back the same power to the source. So although it appears that this reactive element absorbs the power from the source, but in fact it does not absorb any sort of power from the source. So although this reactive element does not absorb any sort of power, but still it draws some current from the source, as well as it will have a voltage drop across itself. So this phantom power which is being absorbed by this reactive element is known as the reactive power, and it is generally denoted by the symbol Q. And the unit of this reactive power is VAR, where VA is the product of voltage and current, and this R represents the reactive power. So in our case, the value of Q will be the product of voltage and current, that is 240 volt with 6 ampere current. So the value of Q will be equal to 1440 VAR. So now so far we have discussed that this reactive element is purely inductive, but the same is true if we have a capacitive load. So in case when we have a capacitive load, then the current will lead the voltage by a 90 degree. But if you see the waveform of power, then the waveform of power will remain the same. So the effective power which is being absorbed by this reactive element will remain the 0. So now let us take the more practical case of a load, where the load have a resistive as well as the reactive element. So let us say in this case the value of resistance is 40 ohm and the value of this reactance is J 40 ohm. So the current I which is being drawn from the source will be equal to 240 divided by 40 plus J 40. So the value of current I will come out as 4.2426 ampere, which will make an angle of minus 45 degree. So now if you see the waveform of voltage and current, then it will look like this. So as you can see here, the voltage will lead the current by a 45 degree, and when we multiply these two waveforms, then the waveform of power will look like this. So as you can see here, for the most of the time the power is being absorbed from the source, but for the small portion of time the power is getting supplied back to the source, and that is because of the reactive element in our circuit. So now for this case, let us find the value of true power as well as the reactive power. So the true power P will be equal to the I square into R, that is 4.2426 square into 40 ohm, which will come out as 720 watt. And similarly the reactive power Q is nothing but I square into XL, that is 4.2426 square into 40, which will again come out as 720 VAR. So in this way we got the value of true power as well as the reactive power. So now let us find the value of a total power or the apparent power. So this apparent power S is nothing but the product of voltage into current, that is 240 volt with current of 4.2426 ampere, and that will come out as 1018 volt ampere. So this apparent power or the total power is having a unit of volt into ampere. So now suppose if you want to represent these three powers on the phasor diagram, then using the power triangle it can be represented. So here this true power is nothing but 720 watt, while this reactive power is 720 VAR, and the vector sum of this true power and the reactive power represents the apparent power. So the apparent power S is nothing but P square plus Q square, and it will come out as 1018 volt ampere. So now if you see this power triangle is very similar to the impedance triangle of a series RL circuit. So in case of the series RL circuit, if you see the impedance triangle, then it will look like this. So now let us say this angle is 5. So we can write cos of 5 as R divided by Z. Now whenever we multiply all the three sides by I square, then this impedance triangle will be converted into this power triangle. So just by multiplying these two terms by I square, this I square R will represent now the true power, and this I square Z now represents the apparent power. So the ratio of true power over the apparent power is nothing but the power factor of the system or a circuit. So in this way this power factor is also denoted by a cos of 5, where 5 is nothing but the angle between the voltage and the current. Now here so far we had assumed that this reactive element is purely inductive, but suppose if we have a capacitive reactance, then this power triangle will look like this. So in any case this power factor will be equal to cos of 5. So now as you can see, whether this load is inductive or capacitive, the value of this power factor will be in the range of -1 to 1. So now whenever we have an inductive load, then the value of this power factor will be between 0 to 1. And whenever we have a capacitive reactance, then the value of this power factor will be between the -1 to 0. So whenever we have an inductive load, then in that case the power factor is known as the lagging power factor, because in case of the inductive load the current lags the voltage, while in case of the capacitive load the power factor is known as the leading power factor, because in case of the capacitive load the current leads the voltage. So that is all about the leading and the lagging power factor. So now let us find the power factor of our given circuit. So we have already seen that this power factor PF is the ratio of true power divided by the apparent power, and earlier we had find the value of P as 720 watt and the value of S as 1018 volt ampere. So if you calculate, then the value of this power factor will be equal to 0.707. So now so far we had seen the definition of this power factor, and we understood what do we mean by this true power, reactive power as well as the apparent power, and we also understood what is the leading as well as the lagging power factor. Now let us understand what is the actual significance of this power factor in the electrical systems. So now in this case if you see, the power factor is 0.707. So the actual amount of power which is being utilized for the work is only 720 watt. But in fact we are drawing the more power from the supplier, that is 1018. So this additional amount of power will go across this reactive element. But suppose if we have a purely resistive element, then the entire power which is being drawn from the supply will be utilized for generating the useful work. So for any system, the value of this power factor should be as close to unity. So when we have a poor power factor, it means we are drawing the additional power for the reactive element across the load. And this additional power means we are drawing the additional amount of current. So this additional amount of current will introduce the voltage drop across the cables. That means we will receive the less amount of voltage at our homes and the offices. So all this thing is basically a additional amount of burden on the power supplier. So whenever we have poor power factor, then these power suppliers used to charge for the poor power factor, which is known as the power factor penalty. So when we have a poor power factor, then the electricity bill of our system will also increase. So that is the reason in industry you will find that the more importance is being given on this power factor. So that is being said, now let us understand how to improve the power factor of any given circuit or any given system. So here we have assumed that our load is inductive, which consists of resistor as well as the inductor. And for the given load, the impedance triangle looks like this. So for the given system, let us say the power factor is cosφ1 and we want to improve the power factor. So now to improve the power factor, we need to reduce this angle, because whenever this angle is 0, then we will have a unity power factor. So to reduce this angle, we need to reduce the value of this reactance. So whenever we introduce the capacitor in our circuit, then the capacitive reactance can be represented like this. So this capacitive reactance will get subtracted from this inductive reactance, and because of that the effective reactance will be reduced, and so the power factor will be get improved. So let us say we have introduced this capacitor in our circuit, and because of that our new power factor is φ2 and the new reactance is X, where X is nothing but XL minus XC. So the value of this capacitive reactance should be such that we will get a new value of this X, that is XC should be equal to XL minus X, that is nothing but R into 10 of φ1 minus 10 of φ2. So if you know already the value of this initial power factor and the improved power factor, then we can calculate the value of this capacitive reactance, and from the equation X is equal to 1 divided by 2 pi Fc, we can calculate the value of this capacitance. So in this way, by introducing the capacitor in the circuit, we can improve the power factor of any circuit or system. So now for our case, let us find the value of this capacitor which will improve the power factor. So earlier we had seen that for this circuit the power factor is 0.707, and let us say we want to improve the power factor to the unity. So now whenever we require the unity power factor, then the value of this reactance should be equal to 0. That means the capacitive reactance should be equal to this inductive reactance. Now we know that the reactive power Q will be equal to V square divided by XL. and here the Xc is equal to XL. So we can write V square divided by Xc. That means Xc is nothing but V square divided by Q. Now we know that here the voltage is 240 volt, that is 240 volt square, and earlier we found that the value of this reactive power is 720 VAR. So from this we will get the value of Xc as 80 ohm, and if we compare this Xc by 1 divided by 2 pi into Fc, then roughly we will get the value of C as 40 microfarad, where here the value of this frequency F is 50 Hertz. So just by introducing the capacitor of 40 microfarad, we can achieve the unity power factor in our circuit. Now let us also understand by introducing this capacitor how our apparent power or the total power will be reduced. So for that we need to find the overall impedance of this circuit. So the overall impedance of the circuit will be equal to this Xc in parallel with this ZL. Now we already found the value of this Xc as minus j 80 ohm. So now this Xc parallel ZL will be equal to minus j 80 into 40 plus j 40 divided by 40 minus j 40. And if we calculate the value, then the impedance Z will come out as a 80 ohm. So here this impedance will be purely resistive, and for this impedance, now if we find the value of this current I that is being drawn from this source will be equal to 240 volt divided by this impedance of 80 ohm, that will come out as a 3 ampere. So now here as you can see, earlier we were drawing the current of 4.2426 ampere from this voltage source, which has been reduced to 3 ampere. And now if you see the power factor PF, that is the ratio of true power divided by the apparent power, it will indeed equal to 1, because earlier we had found that value of this true power is 720 watt and the value of apparent power S, that is equal to 240 volt and 3 ampere current, that will be equal to 720 volt ampere. So in this way now the power factor will be equal to unity. So now whatever amount of power which is being drawn from the supply will be actually utilized in converting the useful work. So in this way, adding the capacitor, we can improve the power factor of any system. So now so far whatever discussion that we carried out, that was for the linear loads. That means the load contains the resistor, capacitor or inductor. But in actual systems, if you see, we used to have a non-linear loads. Like in case of the variable frequency drive or servo drives, we used to have a rectifier bridge or rectifier circuits inside these drives. So because of these non-linear elements, we used to have a harmonics of this current. That means apart from the fundamental frequency of the current, we also used to have the harmonics. And because of this harmonic distortion of the current, we used to have a degradation in the power factor. So now whenever we have a linear loads, then this power factor is known as the displacement power factor, because whenever we have a linear loads, then the degradation in the power factor is just because of the reactive element, because this reactive element introduces the phase difference between the voltage and current, or we can say that it introduces the displacement between the voltage and current. So this type of power factor is known as the displacement power factor. But when we have a non-linear loads, then in such case we also used to get a harmonics of the current, that is a distortion in the waveform. So because of this, whatever degradation that we used to get in the power factor is known as the distortion power factor. So if you see the actual systems, in actual system we used to have both types of power factors, and the total power factor is the product of displacement as well as the distortion power factor. So now in the practical systems, when we have a non-linear loads, then in such case just by applying the capacitor we cannot improve the power factor, because this degradation in the power factor is because of the harmonic distortion. So for that we used to first of all remove this harmonics of the current, and that can be achieved by applying the passive or the active harmonic filters. So in this way, whenever we have a non-linear loads, then by applying the passive or active harmonic filters, we can improve the power factor of that system. So I hope in this video you understood what do we mean by this power factor, what is the significance of this power factor, and how we can improve the power factor of any system. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.